A whistling or humming fan is giving you a clue, not a diagnosis. Aerodynamic, mechanical, electrical, and structural sources can sound surprisingly similar. Before replacing a motor or bearing, capture what changes with speed, airflow, load, and location. If you suspect rubbing, a loose rotating part, overheating, smoke, or severe vibration, stop the equipment and inspect it safely. Record the exact fan model, speed or command, airflow and pressure condition, damper position, filter state, and installation. Keep the microphone at the same distance and orientation, away from direct wind and handling noise. Background equipment can create false tones. A phone recording is useful for comparison, but it is not a calibrated sound power test. A whistle often appears as a narrow, high-frequency line. Look for small gaps, sharp edges, partially closed dampers, grills, seals, or leaks where high-velocity air can form a tone. Do not assume the fan wheel is guilty. Make one safe airflow path change, restore the same duty point where possible, and see whether the tone moves or disappears. A low tonal hum may track electrical supply, drive switching, motor magnetic forces, or structural vibration. The fundamental and harmonics matter, but there is no single universal hum frequency. Compare the sound spectrum with current, drive status, and vibration at the housing. Never open energized equipment or probe electrical conductors unless you are qualified in following the exact procedure. Calculate a hypothesis marker. Blade pass frequency equals RPM divided by 60, multiplied by the number of blades. If a strong tone follows that marker as speed changes, investigate inlet distortion, will condition, blade clearance, and nearby obstructions. A match does not prove blade damage, it only links the tone to a once-per-blade aerodynamic or interaction event. Resonance often reveals itself when a tone grows sharply inside a narrow speed band and falls outside it. The source may be modest, but a panel, duct, base, or support amplifies it. Map vibration at several safe external points and compare phase or amplitude. Do not keep sweeping through a speed that causes severe vibration. Bearing degradation, looseness, imbalance, and misalignment can create tones, sidebands, impacts, or a raised broadband floor. Audio alone cannot separate them reliably. Compare vibration with RPM, temperature, lubrication condition, and the manufacturer's limits. Inspect only after isolation, lockout, and verified absence of motion and voltage. Turbulence sounds more like a wide noise floor than one clean line. Common triggers include blocked filters, poor inlet approach, elbows too close to the fan, abrupt transitions, high velocity, stall, or an operating point far from the intended range. Measure airflow and pressure, because simply reducing speed may hide the noise while leaving the system problem unresolved. Intermittent scrape marks in the waveform can indicate contact, debris, thermal growth, or a shifted wheel, but recordings cannot prove which one. Shut down if contact is suspected. With energy isolated, inspect clearances, guards, fasteners, the wheel, and housing. Do not reach through a guard or use a handheld object near a rotating fan. Move the microphone around the enclosure without changing the operating point, then compare the map with vibration measured on safe external surfaces. A strong airborne hotspot near an inlet suggests a different path from vibration that travels through a base or duct. Flexible connectors and isolators are confirmation tools only when they are correctly selected and safely installed. Test one reversible hypothesis at a time, open a damper to its documented position, correct an inlet obstruction, secure a panel, isolate a known structure path, or use an approved speed step. Return to the same operating point and microphone geometry. If several variables change together, the improved sound will not identify the real cause. Save the model, operating point, microphone geometry, time recording, spectrum, RPM, blade count, current, vibration locations, and every controlled change. Finish by verifying airflow, pressure, current, vibration, and sound, not sound alone. A useful diagnosis connects the audible feature to a repeatable mechanism and a confirmation test. Name the sound, then prove the source.